Hello everyone. In this video, I am going to be going over the common fate model. So the common fate model is a seldom used dyadic analysis that I actually believe is one of the most underutilized dyadic methods. You will see that the actor-partner interdependence model, or the APIM, is published much more frequently um, due to a variety of reasons. It's relatively easy to understand. It's really easy to estimate. It can be estimated in both SEM and multi-level modeling, and it's a highly flexible method. Um, but what we're going to talk about today is the common fate model, which is a little bit less flexible. So the common fate model really needs to be estimated within a structural equation modeling framework because we will be using latent variables. Um, there may be ways in order to estimate this within a multi-level modeling framework, but to the best of my knowledge, I've only ever seen it estimated within SEM. And so one of the differences between the common fate model and the actor-partner interdependence model is the APIM accounts for interdependence, or the dyad members being nested within a relationship, for example, um, through they account for the non-independence through the partner effects and the residual correlations. So in the common fate model, we do things a little bit differently. And so in the common fate model, we're actually going to have a different unit of analysis. Within the APIM, everything's at the individual level. We have person one and person two, their IV and their DV, right? So it's all about each variable is measured for each person, and it's measured at the individual level where every variable predicts or covariates with every other variable in that model. And so what we're going to do that's different here is we're actually going to identify shared variance among the IV and the DV among dyad members. And so that's where the latent variables come in. And so if we're trying to identify what is shared between couples, so for example, when we think about relationship quality, I'm happy in my relationship with my partner, I'm satisfied, all things considered, I enjoy being with my partner, and questions like that are really referencing the relationship. You're going to have person A, you're going to have person B, and there's going to be a lot of overlap there, most likely. It would be exceptionally rare that you would have low covariances between them. Otherwise, they wouldn't be in that relationship, right? And so that rather than that residual covariance that you'd see in the APIM, we actually want to model that non-independence through using a latent variable. And the way we do that is we essentially are going to create kind of a dyadic mean. And so what we're going to do is we're going to have the CSI dyad. So that's going to be at level, for those of you who are multi-level modelers, this is going to be at a level 2. It's going to be relationship quality that is variation that is shared between partners. And so one way to think about it is you have this latent construct of shared relationship quality, and that's theoretically causing partner A's response on the variable and partner B's response on that same variable. So that's what kind of again differentiates the APIM with the common fate. So we believe we have a level 2 process that is happening. So it would be highly consistent with like family system theory, for example. And so what we're going to do is we're actually going to fix these factor loadings to 1. We do that for a couple of reasons. The first is for statistical identification. If you're familiar with latent variable modeling and factor analysis and confirmatory factor analysis, then you probably know that in order to fully estimate a model, you need a latent variable model, you need at least 3 indicators, because that is actually a saturated model where you have no degrees of freedom. And if you have less than 3, you have to impose constraints on the model in order for you not to have negative degrees of freedom, which can't happen. And so what we're going to do is we're going to constrain each of those factor loadings to 1, which theoretically presumes that the latent construct at the dyadic level, that's the part that really gets tricky, at that dyadic level is equally indicated by partner 1 and partner 2. All right. And so we're going to fix those loadings to be 1, and thereby therefore they're going to be equal to one another. All right. So that's what we're going to do on relationship quality. And then we're going to do the exact same thing for relationship mindfulness. All right. So for those of you who watched my other videos, I've been using depression and relationship mindfulness through a lot of the analyses. Here, I have made an intentional switch because depression can't or doesn't exist at level 2. You can have shared depressive symptoms between male and female partners, but that doesn't necessarily mean that there's this relational process on this relational level, this cloud of depression that looms over the relationship and equally affects both partners. And so you might make the argument that there's like a family emotional climate variable, and I think there's a lot of theoretical justification for that. But since depressive symptoms is measured at the individual level, my sadness, my suicidal ideation, my hopelessness, my changes in appetite, we can't really make strong inferences about what's happening at the dyadic level beyond beyond the correlation. And so to me, you're moving too far beyond what your measurement is allowing you to do by using the CESD, which is why I have switched over to the couple satisfaction index for both the CSI and the relationship mindfulness. In the prompts and the questions, it specifically references the relationship, which makes it appropriate for the common fate. Again, this goes back to what I said earlier, that the common fate is less flexible because you have to have a dyadic process. You have to measure something that either affects both partners equally, like a child's cancer diagnosis or perhaps separation and divorce, or it has to be a dyadic process within the relationship, such as communication, satisfaction, perhaps parenting beliefs, and things of that nature. So we're going to do that for shifting back to the model for both CSI and relationship mindfulness. And so this is the simplest common fate model that we can estimate. All right, so this is going to be our measurement model. Again, fairly straightforward, especially if you are familiar with confirmatory factor analysis. All we do is throw a 1 and a star before each of these variables, and that constrains the loading to be 1, or at least I'll say our unstandardized loading to be 1. We'll actually look at the standardized as well. And then we can move on to specifying the 2 covariances in our model. So in the common fate model, we are going to specify 2 residual covariances, but they are not going to be across partner because that's already captured by the latent variable. That's already capturing that shared variation. So there shouldn't be any other shared variation that's kind of left over. So what we are going to do is we are going to capture through residual covariances potential shared variation between the residuals of dyad members 1 report on the first construct and dyad member 1's report on the second construct. So a within person covariance. So for example, here we have couple satisfaction reported by men. It's going to be covariated with relationship mindfulness reported on by men. And then we have the exact same process for women in this study. All right, so essentially that is the most basic common fate model. And what we will do is we'll go ahead and run this. Down here is a very straightforward common syntax that you will see. Here we're creating our fit object, and we're using SEM within the lavaan, the SEM function within lavaan. Then we have our model name, and then we have our data name, which comes from our data object up here. Mean structure equals true, estimator equals MLR. My preference is to use MLR because It provides an adjustment to our chi-square statistic and our standard errors due to non-normality, which we almost always need in the social sciences. So this is actually my default. And then I have missing equals ML to employ full information, maximum likelihood, so we don't listwise delete some of our cases. And then what we're going to do is we're just going to just get our fit measures, our R-squared, standardized. We'll need that when looking at the factor loadings, and then mod indices. Generally, that will not be needed this early on in the common fate, because our common fate will only have 1 degree of freedom. Right, so our fit statistics are either going to be exceptional, it's going to be dang near perfect, or it's going to be kind of really, really off, where our RMSEA is a little higher. Our chi-squares, like with 1 degree of freedom, might even be significant. So there's not really much of a middle ground in my experience. So let's run the model. And so we converged. Right. And so here we have our chi-square statistic, which again, I don't pay a whole lot of attention to. I look more for, is this an indicator of model misspecification in terms of a syntax error, more so than what is actually happening? Because again, I either find values like this, where our chi-square is less than 1, or it tends to be, 6, 7, 8, 9, or 10. Same thing happens in linear growth modeling. So we'll scroll down, everything else looks good. RMSEA is good. Again, I actually disregard the RMSEA in these types of models. Here we are going to look at our latent variables. And so we have them constrained to be 1. But as you may recall me saying, that only constrains the unstandardized loadings to be 1. We still get standardized estimates. And so that's actually going to be really important in the common fate model. And so here's our unstandardized right here. And here is our standardized. All right, so STDL is standardizing both the X and the Y. And so in the common fate, we want factor loadings at 0.7 or higher for on all indicators of common fate latent variables. And we want that because if you go back to path tracing rules, and we want to we want to explain a decent amount of variance that's occurring at the dyadic level. And the way we calculate that is we multiply this factor loading. And so just imagine kind of a path diagram. So you have a latent variable up here, and you have 2 indicators. We're going to go up, 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 up. We're going to go, so you can go backwards. So we're going to multiply 0.855 times the variance of the latent variable. When it's standardized, it's going to be 1. And then we're going to multiply that by this factor loading going back down that arrow. So if we multiply 0.855 times 0.80, that's the amount of variance that is embedded within that latent factor. And so if it's 0.7 or higher, that means roughly 50% of the variance is at the dyadic level and 50% of the variance is at the individual level. Anything lower than that, anything factor loading is lower than 0.7, like if they're 0.6, for example, then are the amount of variance at the dyadic level that is being explained by the relationship is 36%. And if the factor loadings are both 0.50, then it's down to 25% of that variance is occurring at the dyadic level. So we generally want strong factor loadings. And so if these are lower, if they are, say 0.60, that means we might want to switch to a latent congruence model, or we want to model individual variability within the common fate model. And I will, there's another video that I've uploaded that talks about modeling individual parameters within the common fate model. So that's a long-winded explanation for why we want to pay attention to these standardized factor loadings. We really want them above 0.70. And so what we see here is that we have a very strong relationship. So a 1 standard deviation unit increase in dyad level relationship mindfulness that is shared between partners, is associated with a 0.438 standard deviation in relationship quality or variance that is shared between dyad members. In this case, heterosexual couples. All right, so these effects are happening at the relationship level. All right, we'll take a look at the error covariances. Even if these are not significant, I still keep them in the model. Otherwise, we might be playing a game called whack-a-mole where we hit some correlation down and it's going to pop up somewhere else in our model. And so if we even get rid of this, like let's say this 0.185, what's going to happen is that the model is going to try and 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 um, and express this relationship that we have now removed. It's going to be expressed through higher factor loadings and a higher regression coefficient. All right, so I don't necessarily know how high, and actually that's actually one thing that we can test here. But some people are fans of pruning non-significant paths. But especially in dyadic research, I am extremely cautious about doing that, given the levels of interdependence. And so I generally don't do that, even if those pathways are non-significant, just because we will be playing a game of whack-a-mole. And so let's actually get rid of both of them just to see kind of what happens. So we will remove those residual covariances, and we'll keep everything else the same. And I'm not going to throw in a likelihood ratio test. I don't think it's actually all that important here. Rather, the value is really seeing what happens with those parameter estimate differences. So, what you will see here is that here's our model one. So let's go back and memorize, take a quick scan at the factor loadings and the regression coefficients. So it's 0.86 and 0.80, 0.71, 0.75. And then we have 0.44. And so we have 0.854 and 0.801. So again, there's not much change there. Again, here, there's not much change either. I think this one is identical. I think this one was pretty much identical as well. So overall, our factor loadings didn't change a whole lot, which again, probably isn't all that surprising given that they're constrained, especially in the unstandardized effects. But what we do see is this. So before we were at, again, 0.44, if I recall correctly, or 0.438, and now we're at 0.487. So again, there is a relationship between those residuals, between the male residuals and the female residuals, respectively, that's trying to get out. That's trying to be expressed some way in the model, and we're not allowing it to do so through those residual covariances since we eliminated them. And so how that model is now expressing that relationship is through that inflated regression coefficient. Again, even though we wouldn't lead to a substantially different conclusion, this parameter is I would say fairly overestimated, probably by perhaps 10 or 15%. And that can cause big ticket problems, especially if you're closer to p equals 0.05, or when you're testing indirect effects or things of that nature. These can become extremely consequential. So again, you will see some people in SEM pruning those non-significant paths. I cannot caution you more not to do that, especially within dyadic data. So essentially, we down here, the last thing I might go over is the R squared, and this is, we have accounted for 24% of the variance with at dyad levels, couple satisfaction, or relationship satisfaction. So again, our model is doing a really nice job despite only technically having one independent variable in the model. So we're doing again a really stupendous job explaining why people are satisfied in their relationship. So that is the common fate, in addition to a couple other kind of nuances that you will see within dyadic data and structural equation modeling. Hopefully this has been helpful in expanding your knowledge and your ability to estimate dyadic models.